Welcome back. This is week 2 of CS50, and we have thus far been using functions, but largely taking them for granted. We've used printf, which has the side effect of printing things on the screen. We've used getInt, getFloat. But what if you actually want to create your own functions, as some of you might have already begun to do for problem set 1, though not strictly required? Well, let's go ahead and revisit that problem of just asking the user for their name and printing something on the screen, but try to factor out some of the commonality that we've seen in our code thus far. So by that I mean the following. I'm going to go ahead and create a new program, just called hello.c as usual. I'm going to go ahead and give myself include standardIO.h at the top. I'm going to also give myself preemptively the CS50 library so that I don't get yelled at by the compiler. And now I'm going to go ahead and declare int main void. And then in here, this is where I want to begin to outsource functionality to some other function that I myself am going to write, but that doesn't currently exist. For instance, suppose that I wanted to write a function that allows me to print out hello, comma, and then some user's name, right? Rather than continuing to do printf hello, comma, %s, wouldn't it be nice if there were just a function called not printf, but print name? So in other words, I want to be able to write a program that does a little something like this. First, I'm going to say printf your name, thereby prompting the user to give me his or her name. And then I'm going to use the familiar string s to declare a string, give me a variable of type string, call it s, and store in that the result of calling getString. But now in weeks past, I would have somewhat tediously done hello, comma, %s, \n. And in other words, we've seen this example a bunch of times. And it's a trivial example because it's just one line of code. So it's really not a big deal to keep typing it again. But suppose that this line of code actually were becoming a burden. And it's not one line of code, but it's 10 lines of code a couple weeks from now. And you're just getting tired of copying and pasting or retyping that same code. Wouldn't it be nice, instead of doing printf hello, comma, %s, and so forth, wouldn't it be nice if there were just a function called print name that takes an argument? In other words, it takes input, and then semicolon. So that function, wouldn't it be nice if that existed? Then I don't have to worry about what printf is, what %s is, and all of these complexities that are not all that interesting. They are useful. So print name, unfortunately, was not invented some 40+ years ago. No one thought to write it. But that's the beauty of having a programming language. Just like in Scratch, you can define custom blocks. So in C, and most any language, can you define your own functionality? Can you define your own functions? So even though we get main by automatically for free, we can declare our own function. So I'm going to make some room up here up top, and I'm going to declare my own function. That's going to look a little strange at first, but we'll come back to this before long. I'm going to say void, thereby indicating this function does something, has a side effect, but it doesn't return something to me in the same way that getInt or getString itself does. And I'm going to give this function a name of print name. And I'm going to specify that this guy is going to take a string, and I'm going to call that string name. I could call it anything I want, but I want my code to be sort of self-documenting. In other words, if one of you were to open this file and read it, you could sort of infer from the name of that input what role it's supposed to play. And now below that, I'm going to open curly brace and close curly brace. And so notice I've followed the same pattern on lines 4 through 7 as I've been following for a good week plus now between, say, lines 9 and 14, which compose main. In other words, print name is another function. Now, the compiler is not going to know to call this thing automatically, because I literally just invented it. But it will know still to call main automatically. And then, of course, in line 13, I am calling my own function. And because I've declared that function up on line 4 before main, this is going to teach the compiler what quote unquote print name means and what it should do. So I'm sort of giving it a new custom block in the context of, say, Scratch. So in here, I can put that very common or recurring pattern of code I keep writing in class, printf %s, hello, comma, %s, \n, close quote, comma, what do I want to put here? S? So I want to put name in this context. So notice a bit of a dichotomy here. Because I am declaring my own function, and I have somewhat arbitrarily called it print name, and because I've specified in parentheses that this function takes one argument, the type of which is a string, so it's a word, a phrase, something like that, and I'm calling that argument name, that means the only variable that's in scope, so to speak, is name. S only exists between what two curly braces, of course? Well, really just like line 10 through 14. So just like on Monday, cannot use S. But what I can do is pass s into print name. Print name just so happens to give it an alias, a synonym, a nickname, calling it name, and now using it in this line. So now let me save this, zoom out. Let me go ahead and make hello. Looks good, didn't spit out any errors. /hello, enter. What's my name? David. And hello, David. All right, so not all that exciting, but just think now, you now have that same ingredient as we did in Scratch to make our own functions. But there is a bit of a gotcha. Suppose that I hadn't really thought this through, and I actually, without really thinking about it, wrote that function down here. Feels perfectly reasonable. In Scratch, there was no notion of location in your scripts. You could put one up here, one up here, one up here, and it might start to look a little messy if you don't lay it out neatly. But it doesn't matter where physically the scripts were on the screen. Unfortunately, in C, and this is unlike languages like Java and Python and others that you might be familiar with, unfortunately in C, order does matter. Because watch what's going to happen now. The default function that's going to execute is, of course, main. Main is going to call print name on line 8, but unfortunately, the compiler won't even know that print name exists until it gets to line 11, which unfortunately is going to be too late. So let's do make hello. And now, damn, 2 errors generated. So now let me scroll up to the very first, as we should always do, and notice that it's yelling at me, implicit declaration of function print name. So we've seen this message before, implicit declaration of function. When have we seen that kind of error? Well, when I didn't include a library, like if I forgot cs50.h and I would get yelled at for getString or getInt. But in this case, this function print name isn't in a library, right? It's literally in this file. So what's really the problem? Well, unfortunately in C, it takes you so incredibly literally that if you want a function called print name to exist, you either have to implement that function at the very top of your code so that it's accessible to lower functions. But frankly, that becomes sloppy very quickly. Personally, I like putting main first, because then it's very clear what this program does at first glance. And plus, you can get into weird corner cases where if x wants to call y, but y might call x, you just physically can't actually put one above the other. But it turns out in C, we can solve this very simply. I'm going to put a little bit of space up here, and I'm just going to preemptively, albeit somewhat redundantly, going to teach the compiler that there exists a function called print name. It takes a string, and I'm going to call it name, semicolon. So this now in line 4, which we haven't seen before, is a declaration of a function, print name. But it's only a promise that this function will eventually be defined, eventually be implemented. This now I can leave alone because now this is the definition, the implementation, sort of the last mile of the implementation of this particular function. So frankly, it's stupid. It's annoying. But this is the way C is. And it's because it takes you very literally, and as a computer frankly should, only does exactly what you tell it to do. And so that ordering is important. So keep that in mind. And again, start to notice the recurrence of patterns. Odds are you will, if you haven't already, start to encounter messages like this that at first glance seem completely cryptic. But if you start to look for these key words like implicit declaration, mention that it's a mention of a function in this case. And frankly, you sometimes even get a little green caret symbol that tells you where the issue probably is. You can begin to sort of work your way through yet unseen error messages. All right, any questions on writing your own function in this way? Well, let's do something that's a little more compelling. Rather than just do something that has a side effect of printing, let me go ahead and save a new file, and we'll call this positive.c, even though it's going to be a little different versus last time. And this time, I want to re-implement last time's positive.c example, which just forced the user to give me a positive integer. But I had to use getInt last time. Wouldn't it have been nice if there's a function called getPositiveInt that I could just outsource this piece of functionality to? So the difference here is we'll implement getPositiveInt, but unlike print name, which had a side effect, it didn't return something to me, like a number or a string. getPositiveInt is, of course, going to return, hopefully, a positive int. So let's do this. Include cs50.h, include standardio.h, int main void. And now in here, I'm going to go ahead and say, let's say, int, we'll call it n, equals getPositiveInt. And just like getInt already exists, because the staff wrote it, I'm going to assume for the moment that getPositiveInt exists. And now I'm going to go ahead and say printf, thanks for the, let's say, %i \n, close quote, comma, n. All right, so now if I run, or if I compile this program, what is going to happen in my terminal window at the bottom of the screen? Yeah, I'm going to probably get that same error as before. So let's try this. Make positive. And again, implicit declaration of function get positive int. So we can solve this in a couple of ways. I'm going to keep it simple and just put my function, I'm going to put my declaration up here and get positive int. I need the so-called signature. The signature just refers to sort of the aesthetics of the first line of the program. So what should get positive int return? So an int, I mean, ideally it would return something like positive int, but that doesn't exist. We've not seen that among our data types, so we have to kind of deal with the fact that we have very few data types to work with, but we can return an int and just kind of trust that it'll be positive. It's going to be called get positive int. And now how about its arguments? Does it take any input? Does it need any input? So it doesn't need to know in advance anything, right? Get string doesn't, get int doesn't, printf does. It needs to have some input passed into it, and print name needed some input, but get positive int does not. So I'm going to explicitly tell the compiler void. Void is the absence of anything else. So void means nothing is going inside of those parentheses, semicolon. And now at the bottom of my file, and again, I'm just being kind of anal here, putting main at the top, which is good practice, because this way, anytime you or someone else opens your file, the functionality is right there. You can dive in from square one. All right, so now I'm going to duplicate this, get positive int void, but I'm not going to hit a semicolon now. I'm going to open curly braces, and now I need to kind of borrow some ideas for Monday. So as you recall, we did something like do the following while something was true. And what did I do? I did something like give me a positive integer. A little bit of a prompt. I could use any words I want. And then I used what? Int n equals get int. No arguments to it. And notice the difference. When you call a function, when you use a function, you don't put in void. You only do that when declaring a function, teaching the compiler what it should expect. So you don't need to put void there yourself. And now what was my condition? Well, n is not equal to positive, but that's just kind of pseudocode. So how do I express this more cleanly? So less than or equal to 0. So again, notice you can do less than or equal to, even though it's two separate symbols. You can do it on your keyboard as such. But there's still a bug that I screwed up last time, too. Yeah, I have to declare. Exactly. I have to declare n outside of the loop. So I need to put n up here. And I don't want to redeclare it in here, lest I get a new variable. I just want to assign it a value in here. And now I'm not quite done here. Let me sort of get ahead of myself and pretend I'm done. Make positive. And now there's a new error. Control reaches end of non-void function. So new error message, but if you kind of tease apart each of the words, it probably kind of hints at what's wrong. Control. This is just like control just means to the order of operations in a program. The computer's in control and something went wrong. So it reaches the end of a non-void function. What function is it apparently referring to? What function is non-void? So get positive int. And a little confusing in that, well, it's kind of void. It's void. It has a void specification of void for its arguments, but its output is going to be of type int. So the word on the left is the so-called return type. The word on the inside here is the 0 or more arguments that a function takes. So what do I need to do? I've gotten, at this point in my code, line 21, where the blinking prompt now is, I have a positive int inside of the variable called n. How do I give it back to main? Literally, return n semicolon. So just as Colton returned a piece of paper with an answer to me by dropping that piece of paper in the little black box on the table, to do that in code, you literally just write return n. And it's as though Colton were handing me something physical back. In this case, what's happening is get positive int is going to hand back what's presumably a positive integer to whom? Where does that value end up? That ends up in this variable, n. And then we proceed with line 8. So line 9. So in other words, in order of operations, this program starts executing. And the compiler realizes, oh, you want the library? Let me go grab whatever's inside that. Oh, you want the standard I/O library? Let me go grab whatever inside that. What does the compiler say to itself when it hits line 4? Like, oh, you promised to implement a function called getPositive, but we'll get back to that later. Something along those lines. Int main void just means here's the guts of my program. Line 7 is just a curly brace. Line 8 is saying on the left, give me 32 bits for an integer, call it n. On the right-hand side, it's saying getPositive int. Now let's pause that story, because now I don't keep moving my cursor down. My cursor now goes down here. because now get positive int executes. Int n is declared, do the following, printf give me a positive integer, get an int from the user stored in n, and maybe do this again and again, right? This loop means that this code might execute up and down like this again and again, but when the user finally cooperates and gives me a positive int, I hit line 21, at which point the number is handed back, and which line should I highlight now? 9. Control, so to speak, returns to line 9. That's the line that's now in charge. So that's what's been happening all this time underneath the hood. But when we've used functions like printf or even getString that someone else wrote for you, control was being handed off to someone else's code line by line by line. It's just we couldn't see it, and we couldn't really depict it in this program because it's in some other file on the hard drive unbeknownst to us. All right, so let's actually run and compile and run this now. Make positive. Okay, compile, that's progress. / positive, give me a positive integer. Let's be difficult, -1. Okay, 0. Let's give it 50. Thanks for the 50. And so control has now returned. All right. Any questions then on that? Yeah? Say again? Oh, good question. So you might notice a parallel here that I'm kind of cutting a corner on. In line 12, I'm saying get positive int returns an int. But by that same logic, it now stands to reason that in line 6, I'm saying that main returns an int. But what have we never had in any of our programs? We've never had mention of this keyword return. So it turns out that in C, at least the version of it that we're using, made in 1999, technically, this is happening for you automatically. Anytime you implement a program and you implement a function called main, that function will return 0 by default if you don't say otherwise. And 0 is just a convention. The world returns 0, thereby indicating that all is well, effectively leaving us with 4 billion possible things that could go wrong, so that if we return 1, that might signify a code. That means this thing went wrong. We could return 2, which means this other thing went wrong. We could return 4 billion, which means this other thing went wrong. And if you now think about your own PC or Mac, you might recall that sometimes you get cryptic error messages from software that you're using, and sometimes it has like a human-friendly description, but there's often like a code or a number on the screen. If this doesn't come to mind, just keep an eye out for it. That's typically what these codes are referring to. They're included in Microsoft Word and other programs so that if you file a bug report with the company, you can tell them, oh, I got error number 45. And some programmer back at the company can look that up in his or her code and say, oh, that's because I made this bug, and that's why the user got this message. But frankly, it's just a little distracting and a little tedious to conclude that, at least on our first few programs, so we've been omitting it. But all this time, every one of your functions main has sort of secretly had this line automatically added for you by the compiler, just by convention to save you some time. You do not need to include it in main. That's fine. You do need to include it if you were implementing a function like this. Otherwise, the function flat out would not work. But in main, it's not necessary. In a week or two, we'll start getting into that habit once we want to start signifying errors. Really good question. All right. So quick verbal break to mention that this Friday, we won't be having lunch per se, but we'll be having dinner with some of the students and staff. If you'd like to join us, feel free to go to cs50.net/RSVP, 6 p.m. this Friday. If space is, as always, limited, but we'll continue doing these on a nearly weekly basis if space runs out this week. All right. So with the cliffhanger that we left off on Monday was that strings can actually be indexed into, which just means you can get at the first character, the second character, the third character, and so forth, because you can effectively think of a string, like hello, as being, in this case, 5 letters inside of boxes. And you can get at each of those boxes with what syntax did we introduce on Monday? Those square brackets on your keyboard. That just meant go to location 0. We start counting at 0, so bracket 0 signifies H, bracket 1 signifies E, and so forth. And so all this time when we've been using strings and typing in hello and world and other things on the screen, it's been stored in boxes like this. And take a guess, what does each box represent physically inside of your computer? Sorry? So a character, or in the case, certainly in the case of strings, and a character is just 8 bits or 1 byte. So you probably are at least vaguely familiar with the fact that your computer has memory. It has 2 types of memory at least. One is the hard disk, where you save stuff permanently, and that's typically big, so you can have movies and music and so forth. Then you have another type of memory called RAM, RAM, random access memory. And this is the type of memory that is used when your computer is running, but if you lose power or your battery dies, anything that's stored in RAM disappears if you lose power altogether because it's not persistent. You typically have these days a gig of it, 2 gigs, maybe more. And the upside of RAM is that it's much, much, much faster than hard disks or even solid-state drives these days, but it's typically more expensive, so you have less of it. So today's conversation really refers to RAM, that type of memory that exists only while there's power being fed into your computer. So when you type in HELLO, enter on the keyboard, the H is going in 1 byte of RAM, the E is going in another byte of RAM, as is the rest of the word. So recall what we were able to do last time was this. Let me go ahead and open up the file that we called string.c, and recall that it looked a little something like this. Let me actually roll back and change it to exactly what it looked like. String length of s. So look at this program here. We include the CS50 library so that we can use getString. We include standard io.h so we can use printf. Why did we include string.h? This was new on Monday. So we wanted string length, strlen. People decided years ago, let's just be succinct. Instead of calling it string length, let's call it strlen and let the world kind of figure that out. And so that's what we get access to with string.h. This is familiar. This is familiar. This is familiar. This is a little new. In line 22, and we'll come back to this, but for now know, and you would only know this from having read the documentation, or if you knew C already, getString sometimes can screw up. If the user is really adversarial or uncooperative and he or she just doesn't type anything at the keyboard or types so much at the keyboard that it overwhelms the computer's memory, in theory, getString could return something other than a string of characters. It could return a special value called null, in all caps, N-U-L-L, and this is just a so-called sentinel value. It's a special value that signifies something bad happened in this case. It is the absence of a string. So null I'm checking for simply so that, long story short, strlen and other functions that come with C, if they expect a string, but you pass them the absence of a string, if you pass them null, the computer or the program will just crash outright. It will hang. It will throw up some error message. Bad things will happen. So even though this is still not well defined, this will make more sense in a week or two. In line 22, this is just an example of sort of defensive, self-defensive error checking. Just in case one time out of a million something goes wrong, at least my program won't crash. So if s does not equal something bad, I have this for loop. And this was where we had that other new piece of syntax. I have a for loop iterating from 0 on up to the length of s. And then here, I was printing out s bracket I. But why did I use %c all of a sudden instead of %s, even though s is a string? It's a character, right? S is a string, but s bracket something, s bracket I, where I is 0 or 1 or 2, that's an individual character in the string. And so for that, printf needs to be informed that it's indeed a character to expect. And then recall, what did this program actually do? Yeah, exactly. Just printed the word that I type in a column, 1 character per line. So let's see this again. So make string, compiled OK, /string. Let me type in HELLO, enter, and indeed I get it 1 per line. So let me do one optimization here. If you think about it, especially if you've programmed before, there's arguably an inefficiency in line 24. In other words, it's not necessarily the best design. Straightforward, at least once you remember what strlen is, but it's doing something dumb, potentially. What might that be? Exactly. It's checking for the length of s every single time, even though HELLO is always going to be 5 characters. Every time through this loop, the 5 is not changing. I might be incrementing I, but what is the length of s on every iteration of this loop? It's 5, it's 5, it's 5. And yet I am nonetheless asking this question again and again and again. Now, frankly, the computer's so damn fast, no one's going to notice a difference in this case. But these kinds of sort of poor design decisions can start to add up if the compiler itself doesn't try to fix this for you, which it typically wouldn't, at least in the appliance. So I'm going to do this. I'm going to add a comma after my first variable I. I'm going to give myself another variable, calling it n, just by convention for numbers. And then I'm going to assign n the value of string length of s. And then I'm going to change my condition to be what? Whoops. I'm going to change my condition to while I is less than n. So now, how many times am I checking the length of s? once, but it's OK to check I against n again and again, because now those values are not actually changing. Now, for now, just know that anytime you call a function, there's a bit of overhead. Not enough to discourage you really from ever using functions, but certainly when there's a line of code like that, and the lines will get more interesting before long, where there's an opportunity to think, if I type this code, how many times will it execute? You'll start to see over time the performance of your programs can indeed change. In fact, one of the problem sets we've done in years past involves implementing, as you may recall from week 0, a spell checker. But a spell checker that's designed to support a dictionary of 150,000 plus words that we give you guys. You would have to write code that loads those words into RAM, so into boxes like we saw on the screen a moment ago. And then as fast as you can, you need to be able to answer a question of the form, is this word misspelled? Is this word misspelled? Is this word misspelled? And in something like that, what we've done in years past is turned it into, albeit on an opt-in, optional basis, a competition of sorts, whereby the students who use the less RAM and less time, fewer CPU cycles, end up bubbling up to the top of a little leaderboard or ranking that we put on the course's homepage, as we've done in years past. So again, totally optional, but this speaks to the design opportunities that are ahead once we start building atop some of these basic building blocks. All right, so let me go back to this diagram for just a moment and reveal a little something more. This indeed is a string, and we've taken advantage now of a few libraries, standard.io.h, which has printf, among other things, cs50.h, which has getInt and getString and so forth, string.h, which had strlang. But, you know, it turns out there's yet another. Frankly, there's lots and lots of header files that declare functions for libraries. But this ctype.h is actually going to be somewhat advantageous, because I'm going to go ahead and implement one other function, one other program here. Let me go ahead and open up something I wrote in advance called capitalize.c. And let's take a look at how this works. Notice that I'm using, in this version of it, 3 files, 3 familiar files. Notice that in line 18, I'm getting a line of text. Notice in line 21, I'm claiming that the following code is going to capitalize S, whatever the user typed in. And how am I doing that? Well, I'm taking lesson learned from last time. I'm declaring I and N and iterating over the characters in this string. And then what is this block of code in line 24 through 27 doing in layman's terms? Exactly. If s bracket I, so if the ith character of s, which is a char, a specific char in the string, is greater than or equal to lowercase a, and recall that double ampersands signify and the same character, s bracket I, is less than or equal to lowercase z, that means it's an a or a b or a c or dot 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 or a z, which means it's lowercase. What do I want to do in that case? Well, I can do this somewhat cryptically, but let's tease this apart. I'm going to call printf, %c, because I want to reprint this character on the screen. I'm then going to take s bracket I, the ith character in s, and then why am I doing this little trick here? Lowercase a minus capital A. What is that going to give me, generally speaking? Exactly. I don't really remember what, like, it was 65 for capital A. I don't really remember what lowercase a is, but no matter. The computer knows. So by saying lowercase a minus capital A, it's weird to be subtracting one char from another, but what are chars underneath the hood? Well, they're just numbers. So whatever those numbers are, let the computer remember it, and rather than me, the human. So lowercase a minus capital A is going to give me a difference. It happens to be 32, and that would be the case for lowercase b and capital B and so forth. It stays consistent, thankfully. So I'm essentially saying take the lowercase letter, subtract off that standard difference, and that effectively changes s bracket I from lowercase to, of course, uppercase, without my really having to think about or remember what were those numbers we talked about whenever the 8 volunteers came up on stage. Now, meanwhile, in the else, if it's not a lowercase letter as determined by line 24, just print it out. I only want to touch the characters that were actually originally lowercase. So let's see this. Make capitalize, compiled, OK, / capitalize, and let me type in HELLO in lowercase, enter. And notice that it is converted into uppercase. Let me do this again with a different word. How about DAVID with the first D capitalized, as a name typically is, enter. Notice it's still correct. It just outputted that first D unchanged via that else construct. All right, so keep in mind then a couple of things here. One, if you ever want to check two conditions at once, you can and them together as we've predicted. You can compare characters in this way and effectively treat characters as numbers. But frankly, this is so damn cryptic, I'm never going to remember how to come up with this from scratch without sort of reasoning through it for quite a bit of time. Wouldn't it have been nice if someone out there wrote a function called isLower that could answer for me true or false, this character is lowercase? Well, thankfully, whoever wrote ctype.h did exactly that. Let me go up here and add ctype for C types. And now let me go down here and rewrite this line as follows. So if it's called isLower, I claim, s bracket I, then I'm going to delete these two lines altogether. So now someone else, I'm hoping, wrote a function called isLower, and it turns out they did, and they declared it inside of ctype.h. And now I'm going to leave line 27 alone. I'm going to leave line 31 alone. But notice how much I've tightened up my code. It's now cleaner. It's less difficult to sort of look through, because now the function, moreover, is so wonderfully named, it just does what it says. So now I'm going to save this. I'm going to zoom out. And just as in Scratch, you could have Booleans, Boolean values, true or false. That's exactly what isLower effectively returns. Let me rerun with, let me recompile. Let me rerun. And now let's try it again. HELLO, enter. It's pretty good. And try it again. Make sure I didn't screw something up. That is capitalized as well. But this isn't good enough, because the other thing that I'm never going to remember, unless I sort of work through it really carefully on, say, paper, is this damn line. Wouldn't it be nice if there were a function called toUpper? Well, it turns out there is in ctype.h as well. I'm going to go ahead and type, let me bring that line back. Instead of this here, let me go ahead and say, substitute for the %c, the result of calling this function toUpper on the ith character of s. And now notice it's getting a little balanced. I have to keep track of how many parentheses I've opened and closed. All right, so now it's even cleaner. Right now this program is getting better and better designed, arguably, because it's much, much more readable, but it's no less correct. Make capitalize, / capitalize, HELLO. Let's run it again, DAVID. OK, so we're still in pretty good shape. But now toUpper. I propose that there's one more refinement we could make that would be really nice, that could really tighten up this code and really give us 5 out of 5 for design, for instance. What would be nice to get rid of? Well, look how damn long this block of code is just to do something simple. Now, as an aside, as you might have seen in Super Section this past weekend, you don't strictly need the curly braces when you just have one line of code, even though we'd propose keeping them so that it makes much more clear, like in Scratch's U-shaped blocks, what's inside of the branch. But wouldn't it be nice if toUpper, when given its input, turned it into uppercase if it's not? And what would be wonderful in the opposite case, if it's already uppercase? Just pass it through and leave it alone. So maybe it does that. I could try and just kind of hope that it does. But let me introduce one other thing. Instead of using this built-in terminal window down here, recall that this square black icon gives you a bigger terminal window that I can full screen if I want. So it turns out they're sort of oddly named, but there's these things called man pages, manual pages, man for short. And I can access these by typing man, what do I want to type? Man toUpper. And now notice, if there exists a function inside of the computer, in this case the appliance, which is just the operating system Linux, it's going to give me a somewhat cryptic set of output, but you'll find over time that it always is formatted pretty much the same, so you start to get used to it. Notice at the top, toUpper, and apparently this is the same documentation for toLower. Whoever wrote it was cutting some corners and put it all on one page. These things' purpose in life is to convert a letter to upper or lowercase. Notice that under synopsis, the man page is teaching me what file I have to include to use this thing. It's giving me the signatures for these functions, both of them, even though we right now only care about one. Here's now a description. toUpper converts the letter C to uppercase if possible. Still not that instructive, but let me now look under return value, the thing that's handed back. So the value returned is that of the converted letter, or C, if the conversion was not possible. What is C? The original character. And we know that by, again, going up to the synopsis. And whoever wrote this function just decided that the input to toUpper and toLower is just arbitrarily going to be called C. They could have called it most anything they want, but they kept it simple as C. So I've consulted the man page. This sentence reassures me that if it's not a lowercase letter, it's going to just give me back C, which is perfect, which means I can get rid of my else condition. So let me go back to gedit, and now let me just do this. I'm going to copy my printf statement. I'm going to go ahead and right inside the for loop, print that out, and get rid of now this whole if construct. It wasn't a bad idea, and it was very much correct and consistent with everything we've preached, but just not necessary. As soon as you realize some library function exists that someone else wrote, or maybe you wrote elsewhere in the file, you can use it and really start to tighten up the code. And when I say things like good style, the fact that this person called the function toUpper, or previously isUpper, or is lower, is wonderfully useful because they're very descriptive. You wouldn't want to call your functions x and y and z, which have much, much less meaning. Any questions on that series of improvements? All right, so suffice it to say, one of the takeaways is even as your own problem set, maybe problem set 1, but certainly p set 2 and onward, even when they're correct, doesn't necessarily mean they are perfect just yet or particularly well designed. That's the other axis to start thinking about. So this was a string inside of your computer's memory, but if you have a whole bunch of characters like HELLO inside of RAM, and suppose that you, in your program, call getString multiple times, such that you call getString once, then you call getString again, well, what's going to happen over time? In other words, if you have a line of code, albeit out of context, like string s gets, well, let's do this, string name equals getString. So suppose that line of code is meant to ask the user for his or her name. This next line of code is meant to ask the user for his or her school. And this next line, and so forth. Suppose that we keep asking the user for another and another and another string. They're going to stay in memory at the same time. It's not, one is not going to clobber the other. School is not going to overwrite the other. But where do they all end up in memory? Well, if we start to draw on the screen, which we can use this thing here like a chalkboard, if this black rectangle represents my computer's memory, I'm going to arbitrarily start dividing it up into little squares, each of which represents 1 byte of memory. Frankly, if you have a gigabyte of RAM these days, you have 1 billion bytes of memory in your computer, so 1 billion of these squares. So suffice it to say, this isn't really to scale. But we could keep drawing all of these, clearly not to scale, squares. And this collectively represents my computer's memory. Now we'll just do ... So in other words, when I now prompt the user with getString to give me a string, what happens? If the user types in hello, that ends up in HELLO. But suppose the user then types in, actually I shouldn't have done hello because we're asking them for their name. So let's go back if I can do this. Yep. So if I type in DAVID for my name, but recall that the second line of code was getString again to get their school, you know, where is that word that the user types in going to go next? Well, maybe it's going to go into HARVARD. So even though I've drawn it as 2 rows, I mean, this is just a whole bunch of bytes in your computer's RAM, there's a problem now. Because now if I'm using RAM in this very reasonable but sort of naive way, what can you not apparently distinguish? Where one begins and where one ends, right? They're kind of blurring together. So it turns out the computer doesn't do this. Let me actually scroll back in time a few characters. And instead of Harvard going immediately after the user's name, the user actually gets, behind the scenes, a special character inserted by the computer for him or her. \0, otherwise known as the null character, annoyingly called NUL, not NULL, but you write it as \0. It's just all 0 bits, is a demarker in between the first word that the user's typed and the second. So Harvard actually now ends up as this sequence of characters and one more, \0. So in other words, by having these sentinel values, 8 contiguous 0 bits, you can now begin to distinguish one character from another. So all this time, what was hello is actually hello with a \0. And meanwhile, there might very well be quite a bit more RAM inside of the computer. Well, let me do one other thing now. It turns out that all of these squares we've been drawing, they are, yes, strings, but more generally, these things are arrays. All right, an array is just a chunk of memory that's back to back to back to back, and you typically use an array by way of this square bracket notation. So we're going to see these quite a bit over time, but let me go ahead and open up, let's call it ages, and notice what we can do with these same tricks. A little bit more syntax here. So in line 17 of this program, actually, let me run the program first so we can see what this thing does. Let me call make ages to compile this program. /ages. How many people are in the room? Call it 3. Age of the first person, 18, 19, and 20. And now, somewhat ridiculously, I just have made a program that ages those 3 people. All right, so there's clearly an opportunity for some fun arithmetic here. Thankfully, the math is correct. 18 went to 19, 19 went to 20, and so forth. But what's really meant to be illustrative here is how we're storing those 3 people's ages. Let me zoom in at what's going on here. So first, these first few lines should be getting pretty familiar. I'm just prompting the user for the number of people in the room, and then I'm using getInt and a do while to do this again and again and again. We've seen that pattern before. But line 27 is new and actually quite useful and will become increasingly useful. Notice that what's different in line 27 is that I appear to be declaring an int called ages. But wait, it's not just int ages. There's these square brackets, inside of which is n. So the bracket n in this context, not inside of a printf statement here, but in this sole line 27, this line is saying, give me an int, give me n ints, each of which is of type int. So this is a bucket, so to speak, of, in this case, 3 integers back to back to back, so that I effectively have 3 variables. The alternative, to be clear, would be this. If I wanted the first student's age, I might do this. If I wanted the second student's age, I might do this. If I wanted the third student's age, I might do this. And God forbid we need everyone's age in this room. I mean, this is a heck of a lot of copy-paste again and again and again. And plus, once I compile this program, if another student walks in of or out of that door, now my number of variables is incorrect. So what's nice about an array is if as soon as you start feeling yourself copying and pasting, odds are that's not the best approach. An array is dynamic, potentially. I don't know in advance how many people are going to be in the room, but I do know I need n of them. And I'll figure out n when the time comes. This line of code now means give me a chunk of memory that looks like this, where the number of boxes on the screen is entirely dependent on n that the user typed in. So now the rest of this program is actually pretty similar to what we just did with characters. Notice I have a for loop starting in line 30. So right after I get the array, I iterate from I equals 0 on up to n. I just have this instructive printf message that's just saying, give me the age of person, hashtag %i, so number 1, number 2, number 3. And why did I do this? Frankly, humans prefer to count from 1 on up, whereas computer scientists 0 on up. Computer scientists are not going to use this kind of program, so we're going to just start counting at 1 like normal people. And now in line 33, notice the slightly different piece of syntax. The ith age in that variable of type array is going to get an int. And now lastly, this is just arithmetic down here. I decided in a separate loop to claim some time passes. And now in this separate loop, these lines execute. A year from now, person I will be I years old. But notice this isn't the variable I. This is now %i for int. And notice as the first placeholder, I plug in I plus 1. So we count like a normal person. And then for the value of their age, for I years old, I take ages bracket I. And why am I doing plus 1 here? They just aged, right? It's my stupid choice of programs. They just aged 1 year. I could type in any number that I actually want there. So what's actually all of the relevance here? Well, let me actually scroll back over here and paint a picture of what lies ahead. What we'll be doing with our next problem set 2 is dabbling in the world of cryptography. So this is a string of characters, so a sequence of multiple chars. And what does this say? It's not in the online version of the slides. So I claim that this equals this. A stupid advertisement from many years ago. It might actually recall one of its origins. So this is an example of encryption or cryptography. It turns out that if you want to actually send information or share information with someone securely, like a message like this, you can scramble the letters. But typically, the words are not scrambled randomly. They're permuted in some way or changed in some way so that, whoops, that's a fun spoiler for next time. So you can map what is apparently O to B. Notice that lines up capitalization-wise. Apparently, R becomes E. Apparently, FHER becomes SURE. So it turns out there's a mapping. And in this case, there's a pretty stupid mapping, if anyone has kind of figured it out. This is something called ROT13, rotate 13. It is the stupidest of encryption mechanisms because it literally just adds 13 to every one of the letters. Stupid in the sense that if you just have a bit of free time on your hands and a pencil, or you just think it through in your head, you can try all possible additions, 1, 2, 3, ... 25, to just rotate the whole alphabet, and eventually you'll figure out what this message is. So if you did something like this in grade school, passing messages to your best friend, if your grade school teacher simply read through the message and sort of brute forced the solution, you might have gotten an answer by that. Now, of course, in the real world, cryptography is more sophisticated. This is a snippet of text from a computer system that has usernames and passwords, as almost all of ours do. And this is what your password might look like if stored on your hard drive, but in encrypted form. This is not just a rotation of letters, A is B and B is C. This is much more sophisticated, but it uses what's generally known as secret key cryptography. This picture tells the following story with a few icons. On the left, we have what we'll call plain text. In the world of cryptography, plain text is just the original message, written in English or French or any language whatsoever. If you want to encrypt it, we'll pass it pictorially through a padlock, so some kind of algorithm, some function or program that someone wrote that scrambles the letters, hopefully more complicatedly than just adding 13 to each of them. What you get out of that process in the middle there is called ciphertext, so kind of a sexy word. It just means it's the encrypted version of the plain text, and only if you have that same secret, 13 or minus 13, are you able to decrypt a message like that. So in problem set 2, among the things you'll do, if in the hacker edition, you will have to write code to crack these passwords, figuring out what they were and how they were encrypted, though we do give you a bit of guidance along the way. In the standard edition, we introduce a couple of ciphers, encryption mechanisms, one called Caesar, one called Vigenère, that are still rotational ciphers, where A becomes something, B becomes something, but you have to do it programmatically because there will indeed be a secret key involved, which is typically a number or a key word that only the sender and the recipient of these messages should understand. Now, this actually has incarnations in the real world. This, for instance, is little Orphan Annie's secret decoder ring. And you can actually implement these rotational ciphers, A becomes something, B becomes something, with a couple of wheels, one on the outside, one on the inside, such that if you rotate the wheel or the ring, you can actually line up the letters with different letters, getting a secret code. And so as the cliffhanger for today, what I thought I'd do is a bit of throwback that if you turn on the TV on December 24th, you can watch this movie ad nauseum for 24 hours in a row. But for today, I'll open it up here and give us just 2 minutes of a pedagogically relevant, damn it, Christmas story with a little fellow named Ralphie.
Be it known to all and sundry that Ralph Parker is hereby appointed a member of the Little Orphan Annie Secret Circle and is entitled to all the honors and benefits occurring thereto.
Signed, Little Orphan Annie. Countersigned, Pierre Andre. In ink. Honors and benefits already at the age of 9. Come on, let's get on with it. I don't need all that jazz about smugglers and pirates.
Listen tomorrow night for the concluding adventure of the Black Pirate Ship. Now it's time for Annie's secret message for you members of the Secret Circle. Remember, kids, only members of Annie's Secret Circle can decode Annie's secret message. Remember, Annie is depending on you. Set your pins to B2. Here is the message. 12, 11,
I am in my first secret meeting.
14, 11, 18, 16.
Oh, Pierre was in great voice tonight. I could tell that tonight's message was really important.
3, 25. That's a message from Annie herself. Remember, don't tell anyone.
90 seconds later, I'm in the only room in the house where a boy of 9 could sit in privacy and decode. Aha, B. I went to the next. E. The first word is B. S. It was coming easier now. U. 25. That's R.
I'll be right down, Ma. Gee whiz.
T. O. Be sure to. Be sure to what? What was little Orphan Annie trying to say? Be sure to what?
Annie has got to go. Will you please come out?
All right, Ma. I'll be right out.
getting closer now. The tension was terrible. What was it? The fate of the planet may hang in the balance.
No, Randy's gotta go! I'll be right out, for crying out loud!
Gee, almost there. My fingers flew. My mind was a steel trap. Every pore vibrated. It was almost clear. Yes, 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 yes.
Be sure to drink your Ovaltine. Ovaltine? A crummy commercial? Son of a bitch.
This is CS50, and that will be problem set 2. See you next week.
At the next CS50, this happens.
So one topic we haven't looked at thus far is that of function pointers. Now, a function pointer is just the address of a function, but much like... Son of a